A collapsible balloon for carrying meteorological testing instruments aloft is partly filled with 626 liters of helium, measured at 25 degrees C and 756 torr. So let's go ahead and write that down. So we have helium, gas, 626 liters, 25 degrees C, and the pressure they gave us, the pressure, (756 torr). Torr is the same as what? Millimeters of mercury. A millimeter of mercury and a torr are exactly the same thing. Your book likes to use torr a lot. Assuming the volume of the balloon is free to expand or contract according to changes in pressure and temperature, what will be its volume at an altitude where the temperature is minus 58 degrees C and the pressure is 0.641 atmospheres? Minus 58.641. Oh, 258. Okay. Oh, there's an answer. It sounds like there's a mistake in the answer key. Is that correct? And so that's what this particular problem came up. But why don't we get the correct answer? So this is what we'll do. We'll make this a quiz. How about that? A quiz question. Actually, we're going to have a number of quiz questions just for practice. And so can you get like a sheet of notebook paper? And then we'll do this one as the first one. And let's see what people get, since if the answer is wrong in the book, we might as well get the correct answer. Get the correct answer. So this quiz is like a normal quiz. You can work with other people. Do a problem like this on a test. More like probably 5 minutes. It just takes practice. Just more practice you do, the better. I'm sorry? 700.8 liters? Okay. Is that the same number you guys got? What did you guys get? What? 423 liters? Anybody else? What did you guys get? 701? Anybody else? Well, basically, we have to resolve this. You know, there are 3 different answers, maybe more. And so in this case, the solutions, I guess the solutions manual had something wrong with it, so we don't have the answer. But regardless if we have the answer or not, the way we should correct, at least the way we should find out what the correct answer is to do a peer review. Do you know peer review? Uh-huh.
Well, what happened was that we're given a different number in the problem, but we have the answer for this problem.
Oh, we have the answer for this problem?
So we do know that one, but we don't know the answer for the one that we have in the text.
We should have done that one. But it's okay. Let's verify this one. And so what you want to do is you want to compare your work with other people's. In other words, what you want to do is you want to assume that you're correct and the other person's wrong. So what you have to do is you have to convince the other person that your answer is correct. Could you do that? Uh-huh.
Okay, so I got 700.8 liters, but whoever got 701,
They probably just rounded it.
I'm like, did they round it? I'm like, and was I supposed to round it?
Well, it depends for the sig figs. You could just take a look at how many sig figs you're allowed in the calculation and then determine it. It's not going to tell you. You have to figure it out yourself, how many sig figs are allowed. Yeah.
But how would I figure out how many sig figs I'm allowed?
Because you would know the rules for the sig figs. You'd have to know how to count them and then what to do with them. But you could compare with other people, see what they got. Uh-huh.
So for the pressure conversion, would I convert from like secures to atom or atom to fluid? Which is the preferred?
It doesn't matter. Yeah, either way. Atmospheres to torr, torr to atmospheres, doesn't matter. They just have to be the same unit, that's all. Do you know which one of these is right? So far, it looks like 701 is correct because we have two groups that have gotten that, but maybe they aren't. Maybe what you should do is you should check. You should check your number and your work with other people around here. What's that? Okay, for those of you who are getting completely stuck at the first step, what would you recommend to for those of you who had gotten the start? What do you recommend? This is a gas problem, and so we need an equation for the gases. And there's only one equation that came from chapter 4. Actually, there are two, Charles' law, but Charles' law got engulfed by a bigger law. What was the bigger law called? The combined gas law, and you need to know the form of the combined gas law. The combined gas law, somebody tell me what it is. Yeah, P1 times V1 over T1 is equal to P2 over T2. So we're going to call the first row here 1, the initial. And then we're going to call the second row 2. So what are we solving for here? We're solving for V2. So if you're really stuck, you solve this algebraically for V2. But the way I solve this is like this. V2, I get it in ratios. V2 is going to equal P1 over P2. This is called a pressure fraction. And so if the pressure goes up from 1 to 2, then the pressure fraction is less than 1, so that means the volume goes down. So if the pressure goes up, the volume goes down. Do you see that? Because it'll be a fraction. And then we're going to do the temperature fraction. Actually, did the pressure go up or did the pressure go down? I don't know, because if you look, 756 torr is awfully close to 1 atmosphere. So it looks like we went down. So if we If we go down in pressure, that is P2 smaller than P1, then this fraction is greater than 1, which means the volume should expand. And so by the pressure going down, the volume goes up. That's the pressure fraction. Let's take a look at the temperature fraction next. The temperature fraction is going to be T2. It's going to be T2 over T1. So if the temperature goes up, what happens to the volume? So if we go up, that is T2 is greater than T1. That means the temperature fraction is greater than 1. That means the volume has to go up. Whereas if the temperature goes down, T2 is smaller than T1. That's a fraction less than 1. And so it's going to go down. In our case, did the temperature go up or down? Did the temperature go up or down? Oh yeah, the temperature went down. We went from 25 to minus 58. So if the temperature goes down, the volume should contract. As the pressure goes down, the volume should expand. So we have two competing things. The pressure wants the volume to increase. The temperature wants the volume to decrease. Who wins? So we'll see. And then this is going to be multiplied by V1. So here's the impact. So here you can get started here. If you're completely stuck, we want to write out the one. This is the one law. We have a whole bunch of conversion factors from chapter 4 as well. Now you have to show your work. When you do these calculations, just don't write the final answer. If you write the final answer and the answer is wrong, you get 0 partial credit. But if you show your work and it's fairly easy to follow, then you're going to maximize the partial credit even if you get the wrong answer at the end. So make sure you show your work, and that includes writing the units. Because sometimes if you have the incorrect units, you can catch your own mistakes. Whereas if you have no units there, it's very difficult to catch your own mistake. So if you got 701 or 700.8, maybe you can convince the others. Or if you have 423, maybe go find somebody who got 700.8 and compare how they solved it versus how you solved it. Maybe you're missing something, maybe they're missing something. We don't know which one's correct. Just because we have 3 groups that got 701 doesn't mean that's the right answer. And so why don't you do a little bit of comparison? If this were timed, let's say I only gave you 5 minutes to complete this, what would you do? You try to get it done, right, and correctly. So did anybody else get a volume that they want to share? So what's the correct answer, Ashley, in the book? 701 liters. Okay. So here the consensus was 701 liters. So if you didn't get 701 liters, take a look at how people who did get 701 liters might have done it compared to how you did it. All right, so you'll finish that one up. Since a lot of people are done with this, let's go on to the next question. This is going to be the next quiz question. So this is, let's say that's number 1 up there. This will be number 2 here. If you have a car tire, do you know what the pressure is supposed to be? 35 psi? 35 psi sound right? Okay. We'll go with a car tire at 35 psi. And, you're supposed to inflate the tires when they're cold or when they're hot? Cold meaning not refrigerated, just cold meaning room temperature. When you inflate these, you're supposed to inflate them cold. So this is called the cold tire pressure, or the cold air inflation tire pressure, or whatever they call it. And that's not really that cold. In fact, this is, let's say it's room temperature. So room temperature is kind of too warm, isn't it? So maybe you're over there at wherever, Costco or the gas station or someplace, filling air in there, and you put in 35 psi. And then do you know what happens after driving? So you go drive this. Let's say you drive it from here up to Big Bear or something like that on a summer day. This would be a summer day, 77, let's say. Do you know what happens to the temperature of the tire as you're driving it? Yeah, the temperature goes up. Do you know how hot? Have you ever felt a warm tire? Maybe, maybe not. I have, and it gets pretty hot. How hot after driving? Let's say you drove it up into the mountains or something. There's a lot of braking and a lot of turns. It doesn't really expand. Does it expand like a balloon? No, it's because it's got heavy duty construction, which prevents it from expanding. There's steel belts in here, and there's maybe carbon fiber mats, whatever. And so let's say the tire warmed up. Let's say it warmed up pretty hot. How hot do you think you want to go? Let's just pick an easy number. Let's say it got to 100 degrees C. So the temperature increased from 25 to 100 degrees C, and the pressure will increase to what? So the cold, the tire has 35 psi. Hot, how many psi does the tire have? And let me tell you, the volume might change a little bit, but not much, not enough to be significant. So what we're going to say is that V2 and V1 are about the same. It's really hard to blow a tire up like a balloon. You aren't going to get the volume to change much. So I want the hot tire pressure versus the cold tire pressure. Sometimes I go put air in my tire, after driving, and the pressure is a bit higher. So I factor that in when I get the air. Okay, so this is question number 2. So if you haven't finished 1, just go ahead and finish 1 and tell me what you got. We know the target, what it should be. It should be 701 or 700.8. We got to figure out how many sig figs we're allowed. And then go on to this. Let me resume this. So how do you prepare for tests? This is how I would prepare for tests. I would go through my notes and make sure I understand everything in my notes. That is every concept that was discussed, like on the PowerPoints or whatever. And then every problem that we did in class, I would make sure I understood completely. And not only that, I would go through it every day. So hopefully I get it done soon so I could go through it like, 5 times, 10 times, 15 times before the test. By the 15th time, it's like driving to school the 100th time. You've done it so many times, you start to notice other things about it. And so that goes for something like this. Some people will go through this. I posted the key to this, and then they'll just kind of memorize the answer here. But what you want to do is, this is like the 100th time. This is like when I was taking history of French film. Did I tell you about that? Yeah, that was a fun class, history of French film. But I thought, what a waste of time watching a movie twice. You think, you've already seen it, you already know the plot. Why watch it again? Why watch it again is because the second time you go through it, you start to notice so many things you didn't notice the first time. And so that's the same thing that happens with these problems. Why go through it again? You already know it. It's B, But it's not that. It's like the law of conservation of mass was derived from theory. Is that true or false? It's false. But then you start to think because you've seen that. Okay, I know it's false, but why is it false? In fact, the law of conservation of mass was not derived from theory. What was it derived from? Observation. Good. It was derived from observation. And then you start to think, okay, is that all you need to know about law of conservation of mass? What else do you know about law of conservation of mass? Could you connect it to something else? Well, you might connect it to Lavoisier. Remember Lavoisier was what did he write? He wrote the principles of chemistry, and he was credited with what? See, these are the kinds of connections you want to make, by going through it. You might not have noticed it the first time you went through it because you just thought false. But the more times you go through it, the more times you have time. You have the leisure of thinking about this. This is like I was watching this documentary. They have the 10 most important chemical reactions in civilization. Have you ever watched any of those YouTubes? So I'm kind of curious, what 10 reactions did they select? And so one of the reactions they selected was the cooking of limestone. The Romans did this. The Romans had coal, and they'd heat up these coal ovens until they reached extremely high temperatures, and then they'd shovel the limestone in them. And do you know what they made? They made calcium oxide, and the calcium oxide was used to make Roman concrete. Now, Roman concrete is structurally some of the best concrete, that you can get. If you go to Home Depot and you buy the concrete there, it's not as good as some of that Roman concrete was. And so your concrete structures aren't going to last like the ancient Romans did. But they're saying, how come the Romans were able to develop that, whereas many other civilizations weren't? The Romans they were well advanced, apparently, compared to others. And what they said was, they had the time to do these kinds of experiments because they had a stable food supply. Since they had a stable food supply, they didn't have to spend all their time foraging for food, and they had more time to spend thinking about these things. Well, the same thing goes here. If you cram this all in one night, are you gonna remember much of it? No. What you need that time, and so the time involves going through it. And so, number one, I would go through my notes and make sure I understand all the concepts that were discussed in all the calculations. Now, if I have additional time, then I would go through. Well, maybe I'd go through the old exam first. If I had additional time, then I'd go through the homework, and then just repeat. And so it's like the film class, except you don't watch it once, you don't watch it twice, you watch it as many times as you can, and that's how it clicks. And so, can you make a connection? What else do we need the conservation of mass for? So what we want to do is, and I mentioned this before, did I talk about one neuron has how many connections? Well, okay, now we have one concept, law of conservation of mass. Tell me all the connections that you can make with law of conservation of mass. Uh-huh.
Did you think 62.2 for number 2?
No, 62.2 I didn't get. Sorry. Just keep at it. Huh? I can solve it, but the thing is, I don't know. Do you think somebody I want to learn to play the violin? Do you think I can watch somebody play the violin and then they show me what to do with my fingers and the bow or whatever else, and then there's the book has the answer, yeah, and then it's. So what you want to do is, I could solve it, but you got to make sure that you just don't leave it at that. What you want to do is you want to go back through and make sure you can solve it yourself. So I'll do it later. If you guys are completely stumped, maybe I didn't give you enough time.
I got 44, so I'm not understanding.
I got 44 too.
I just want to watch you.
Okay.
So I just want to check where I'm going wrong.
All right, so this is what I do. When I go back through, I do this kind of stuff and try to make as many connections as possible to see. Now, I don't know. Did I solve this problem in class yesterday? Number 24. I did solve that in class. It didn't make any sense. If it didn't make any sense, then you want to make sure it makes sense before the test. Because if I do a problem in class and I give you a similar problem, or maybe even the same problem, and you can't make that connection, then you haven't looked at it enough. You need to look at it again. And so like number 24 was very similar. Let's take a look at this one since you guys are curious. Have you given up then? I think we've given up. It's already been an hour. 48, you got it. That's good. So you got 48. Can you just write down how you did it on the board, and then we'll see. Um, yeah, just right there at the left of the, or the right of the screen. Geez, the black pen is good, or the brown. Let's see if I have a black pen. Here's some other pens in case. Let me resume the recording here. That means the pressure goes up. Temperature goes up, pressure goes up. However, the volume, if you look at the volume, if the volume goes up, the pressure goes down because the volume's inverted relative to the temperature. V2 is on the bottom. But did the volume change at all? No. And so if we look at this, V1 and V2 are the same, so they cancel. And this is going to be P times P1. Well, we just calculated P1 in absolute. P1 in absolute is going to be 49.651. And so this is going to be 373, the Kelvin cancels, over 298 times 49.651. PSI. This is PSI A. And so let's go ahead and calculate it. I'm just going to carry the digits in my calculator, times 373 divided by 298. And what do you get? Actually, I miskeyed this. 373 times 49.651 divided by 298. And I get 62.147 PSIA. But do tire pressure gauges measure PSIA? No, our gauges don't measure because they're calibrated to read 0 when the pressure is the same as atmospheric pressure. And so in order to go from this, and so how do we go from Celsius to Kelvin? We use this equation. But how do we go from Kelvin to Celsius? We subtract 273. Well, how do we go from PSIA to PSIG? We subtract. And so PSIG is equal to PSIA minus PA, the atmospheric pressure, which is going to be 14.651. And so this is PSIA. So if I want to calculate the PSIG, I do 62.147 minus the atmospheric pressure, which I calculated. This is slightly less. So this is PSIA minus the correction. So I'm going to just do minus 14.651. That gives me 47.496. Now I have to round this up. This is going to round to what? Actually, I got to keep track of sig figs. So let me back up and let's look at the sig figs for right now. Here, how many sig figs do I have in 373? 3 in 298, 3 in 49.65, 4, but I showed 5 because I wanted to minimize round off. So how many are we allowed here? We're only allowed 3. Because when we do multiplication and division, it's based on the fewest number of sig figs. So I'm only allowed 3. So this should be, I should do this. What I'm going to do is I'm going to subscript the 4. I'm going to still carry it just to minimize rounding in the calculation. But I only have 3 sig figs here. And so now I have to do this to 3 sig figs or round this. What would this round to 3 sig figs? Yeah, 47.5 PSIG. It depends on how you round things. You know, if you round this to 2 sig figs, 48 PSI. But officially we would be allowed, looks like 3 sig figs in this particular calculation. So 47.5 PSIG. Okay, the small difference in atmospheric pressure didn't really alter the answer much.
Why don't we acknowledge like 100?
Why don't we acknowledge, I'm sorry?
100 degrees Celsius.
100 degrees Celsius. We do. 100 degrees Celsius is the same as 373 Kelvin.
Isn't that 1 sig fig though? For the 100?
Oh, I see what you're saying. 100 degrees C might be 1 sig fig. That's true. It could potentially be 1. It's ambiguous. And so if you have 100 degrees C, to make it less ambiguous, I put a little period there at the end. And now it would be 3 sig figs.
Yeah. So you just assume that it's like 1 right after reading that case?
You would have to read the problem to see what the precision is. The reason I'm thinking the precision is a little bit more precise than that, if it were just 100, then we'd be counting 100, 200, 300, 400. You know, 1 sig fig means that. But the other temperature was 25. That was to the nearest 1 degree C. If we're using the same thermometer, it would read to the nearest 1 degree C. So therefore, based on the 25 and using the same thermometer, I would expect it to be reading to the nearest 1 degree C, which would make that 3 sig figs. And so that's how I inferred it was 3 sig figs.
Okay, and then for the homework, there was like a problem in chapter 3.
Uh-huh.
And the only context it gave us was that it was 48,000 centimeters of wire.
Oh.
But it says uncertain 1 to 3 digits. So I don't really understand why you couldn't just say like uncertain.
What was it, 40,000 centimeters of water?
It was 48,000 centimeters of wire.
Of wire. This is ambiguous. It's ambiguous because what's the population of this town? Oh, there are 48,000 people in the town. You know, how precise is that? Did they count everybody and they got right on 48,000? Maybe they counted every single individual in there and it came out to 48,000, not 39,999 and not 40,001. It came out 40,000. And so in that case, it would be 5 sig figs. But it's a little bit ambiguous because, hey, they might have just, you know, counted roughly and said it's about 48,000. And so we don't know. We need further information to determine. So what do you do in a case like that is you say it's ambiguous. It could be 2 sig figs or more. In Chem 1A, the way we'd answer this particular problem here is it might be 2, 3, 4, 5, or infinite sig figs. It could be infinite sig figs because you might say in exactly 48,000 centimeters, you know, how many meters are there? You know, and so it's okay that it's ambiguous. You know, other times if it's ambiguous, what we do is we usually go with the more, and so we just treat it as being more, and then we can get more digits at the end. We don't go with fewer because that's going to give us more rounding error significantly. All right, but do you see that this problem is very similar to the problem on the left? It's almost the exact same thing, and we did the exact same process in solving this particular problem. Okay, we can take a break, and then we're going to have another problem coming up here next. We're going to have Can somebody write how they solve this one on the board? You want to do it? I want to see how you set it up, especially with the tax. Yeah, go for it if you don't mind. There's some black pens there. All right, take a picture of this. Well, you have this problem in the book, so. Actually, how much time do we have left? 15 minutes? 50 minutes? Okay, we're good. All right, try this problem next. The volume of seawater on Earth. Thank you. Does anybody else have a different method that they use here that you can share? You want to? Danny, you have something? Yeah, go for it. All right, does anybody else have a different method that they use to solve this? All right, be careful when you do this because if there are no units here, then it's a little bit more difficult to follow. So we're starting to lose units here. And then 7.6, x is equal to 7.6 what?
Okay.
So you need to write the units here.
Right.
So 7.6 weeks here. At least have the units at the end. But you got to be careful here because it's a little bit harder to follow than this. This is a little bit easier for me to follow. Except, is this, did you get this? One shift is 1 hour, is that right? Is each shift 1 hour? Each shift is 4 hours. And how many shifts per week? 5 shifts per week. But the answer is correct. But the situation is, though, in this, if you don't show your work, I don't give credit for it. And even if the reason I don't give credit is because sometimes people get the correct answer by making 2 mistakes, and 2 mistakes that effectively cancel each other out by luck. But if there was another problem, that luck would have run out. And so I would check the work to see here. This is wrong, but how are they getting this? But is it you just forgot to write it? Yeah, that's fine. Good figure. So you had it right. You just got to be careful with that. Okay, now it looks good. The other thing is, this is good to have a separate calculation here. I like this. But what I like to do is, if we have a percentage, I'd like to include it as a conversion factor down here. And so what we can do is, and this is the way I probably would have set it up. This is slightly different. I mean, all these look like they work. We get the right answer there. But I probably would have set it up like this. So we have 23% tax or withholding. If we have 23%, let's convert it to fraction. How do I convert percent into a fraction? Yeah, 23 over 100. And so it's going to be 23, but it's going to be 23% what? It's going to be $23 withheld. $23 withheld for every $100 earned. So if $23 is being withheld, how much is your take-home pay? 77. So that's good that you figured it out. It's going to be $77 take-home pay for every $100 earned. And what we're going to call this is we're going to net $77 for every $100 gross. Now, this is the conversion factor that I'm going to use down here. And so I'm going to start off with the fixed. The fixed cost is $10.80. How much was it? $10.8249. So I would have gone $10.8249. And then is this, can I pay for this with gross dollars or net dollars? Yeah, I have to pay for this by net dollars. And so that means I need to earn $100 gross for every $77 net. And so what I'm going to do is I'm just going to include this as a conversion factor in the problem itself. And so the net dollars cancel. That gives me gross dollars. Is the pay in net dollars or is the pay in gross dollars? The pay is in gross dollars. And so it'd be $925 gross dollars pre-tax for every hour that was worked. And then the rest would be the same. One shift is 4 hours. And then there are 5 shifts in a week. And then we're done. Okay. Now, this problem it depends on this. You know, if the schedule's per week, then we'd have to work in whole weeks. And so if you get 7.6, then, and they're asking how many weeks, that's okay. We could say 7.6 weeks. but they aren't going to receive that check until they work the 8th week. And so in this case, we're just going to round it to 8 weeks, even though we're allowed more sig figs probably, although the shifts might vary. The shifts might sometimes be a little shorter or maybe a little longer. I don't know. And so here we're not really paying attention to sig figs that much. All right, since we have some time left, we can get some more practice here. And so let's try out another seawater problem. Try out number 71 here. This is like trying to climb Mount Everest one step at a time. So we start off with a fixed quantity. What's a fixed quantity here? Something that's not some ratio. It's fixed. We call those things extensive versus intensive. Like 3.5% is intensive. It doesn't matter how much ocean you have, it's always 3.5%. The density is intensive. Does it matter if you have a little ocean or a big ocean? No, it's still always going to be 1.03. 330 million cubic miles. Is that extensive or intensive? It's extensive. What does extensive mean again? Can you define extensive and intensive for me one more time?
Extensive is like a ratio.
Okay.
Extensive is just like what it is.
Okay, I'll go with that. Good enough. The way I define it is intensive means independent of the amount. It doesn't matter how much you have, intensive is independent. Extensive is dependent on the amount. So volume's extensive. This is volume. So if you have 1 gallon versus 2 gallons, it depends on the amount. Whereas if you have 1 gram per milliliter, then it doesn't matter if you have a gallon of water or 2 gallons of water, it's still 1 gram per milliliter. So we start off with this. A lot of people leave the page blank, but at least write one thing on the page. Some people, they look at the whole problem and it's too much to gauge at once. You don't have to gauge the whole thing at once. You don't have to see the whole problem. If you don't even look at the summit of Mount Whitney, if you go to the base of Mount Whitney and look at not Mount Whitney, Mount Everest and look at the summit, it's too much, right? It's overwhelming. But if you go to the base and just take one step up, then it's doable. So this is the first step. If you can't write this down, then figure out how you can do it. Figure out how you can take this step. Now, the next step up is to get rid of miles cubed, but I don't know anything that gets rid of miles cubed, right? But we know if I just find something that gets rid of miles and cube the whole thing, I'm okay. So this is the next little step. But the problem is I got to find something that takes me from miles to something else. I can go from miles to kilomiles. Do you think that's the right direction? I can go to miles to millimiles. Should I go from miles to millimiles? No. I probably want to go from miles to feet. And how many? This one you don't have to memorize. They're exactly 5,280 feet per mile. And this is not a nautical mile. A nautical mile has over 6,000. So if we do this, that means we have to cube everything. That's 5,280 cubed. A lot of people forget to cube it in their calculator. It's not 5,280, it's 5,280 cubed, which is 5,280 times 5,280 times 5,280. So some people write it out. They'll write out 5,280 feet times 5,280 feet times 5,280 feet. And then below here, they'll write 1 mile times 1 mile times 1 mile. And then that's it. This is this. But I don't want to write it out. I'd leave it. So it depends on how many steps there are. If you do one step, that's better than doing no steps. And so you can get some partial credit by doing this one step. And so what do you do? We went from cubic miles to cubic feet. Now we have to go from a feet to something else. But I don't know cubic feet, but I know feet to something else and then just cube the whole thing. And so how many different choices do you have? You could go feet to yards. You could go feet to inches. Give me another one. I don't know feet to centimeters. I don't know feet to centimeters because I want to keep the amount of memorization to a minimum. And I don't want to Google it because I'm not going to be able to Google things on exam. So I'm not going to go feet to centimeters. So I only have two choices. And it doesn't matter. I'm going to go feet to yards. So I'm going to go from how many? 3 feet and 1 yard. Okay, and now the cubic miles cancel, the feet cancel, now I'm in cubic yards. Now where can I go? How many things do you know for yards? Seriously, how many things do you know for yards? Well, some people go, oh, okay, I can go yards to whatever, but they'll have to Google that. I don't want you to Google that. I want you to do it based on the ones you have to memorize. And so, the only thing I know is 1 yard is equivalent to 3 feet. So this is like you're in the jungle. You take this path, and then it's like, wow, I'm back where I started, right? But that's no big deal. I don't really care because there's another fork there. So this one turned out to be wrong. This is going in circles. So what I'm going to do is I'm going to take an alternate path. What's the alternate path? Well, I didn't have many choices. I could go feet to yards or I could go feet to inches. And so they're 12 inches and 1 foot and then cube the whole thing. I don't know where I'm going. This is why I went in a circle, but that's the whole point. Problem solving is like that. Problem solving is supposed to be difficult. If it were easy, then you wouldn't need a brain to do it. They could just have, well, AI is getting pretty good at doing things, but still AI is not good enough. But you think about it. If a problem is so easy that anybody can do it, including a kindergarten, who's going to hire you to do anything? Or, what unique thing do you bring? If somebody like an elementary school student can do it, then there's nothing special. And so what you got to do is you got to think about this and but we don't necessarily know where we're going. But here, going to inches gives us more options because from inches, where can I go? Centimeters. And then just continue on. So it doesn't matter. You have a limited number. It's not an infinite number of choices. You have a limited number of choices. Try them all because you have plenty of time. Remember I told you, how much time did I give you to solve these problems? Way more time than you would have had on a normal exam, And so what I'm going to do tomorrow is I'm going to use the full 3 hours. The exam's like 1 hour exam. Some people are going to finish super early. If you finish super early, you want to go back and double check your answers. Some people will take the whole time and not finish early. If you don't have time to double check your answers, just at least try to finish as many problems as you can. But the exam, you have plenty of time. This is my dilemma. My dilemma is I don't like timed exams. I used to hate timed exams when I took them, because I thought, if I just had a little bit more time, I would have gotten that problem. And so I've never liked them. But unfortunately, so many exams are timed. And the problem is they write too many questions for the amount of time that you have. So that was always frustrating. I never liked that. But then, so I went the opposite. I try to give lots of time so you can go back through and figure things out. But that hurts you in the long run. It hurts you because when you leave here and go there, they're probably going to have timed exams. And so what are you going to do? You haven't properly trained for timed exams with that time pressure, bearing down on you. And so you want to think about that. Tomorrow, hopefully you'll have plenty of time. You could if you go down the wrong path, no big deal. Back up, try a different path. But look how much partial credit you would have gotten here because you were able to do, you're on your way, you're well on your way to solving the problem, You've gotten a lot more pressure, partial pressure than just giving up, before taking the first step. In chapter 4, pretty much it's finished. Chapter 4 is just pressure measurement, manometer, barometer, and the combined gas law. P1 V1 over T1 is equal to P2 V2 over T2. That's it for the part 1 of gases. Then we're going to hit gases one more time. And when we hit it again, then we'll look at it in more depth. But
Sorry, we're not responsible for like the pressure units and conversions.
no, you're responsible for that. Like, for example, we converted from atmospheres to PSI. You have to do those kind of conversions. You're not responsible for memorizing which ones. So what did I say yesterday? The ones to memorize. You need to memorize that 1 atmosphere is 760 millimeters of mercury exactly. Your book likes torr, so that's an easy one to memorize, the torr. But I don't particularly do much torr. And do you have to memorize pascals and bar? No, 1 atmosphere is 101,325 pascals. You don't have to memorize that. But those are just dimensional analysis. The dimensional analysis is the same conceptual, like problem solving that we did in chapter 3. And so those pressure conversions are just part of the homeworks there. And so chapter 4 is pretty much done. It's just the combined. I skipped Boyle's law, I skipped Gay-Lussac's law, I skipped all the simpler gas laws because we don't need to know those. We just need to know the combined gas law. That works for everything. The open-end thermometer, there are only 3 scenarios. The open-end manometer. So this is what you do when you go back and review this stuff. We have 2 where the seesaw is tilted and then 1 where the seesaw is balanced. So if these 2 liquid levels are equal, we say that the pressure is equal. That's what we did with our flask. We made the liquid level inside the flask in the Charles' law experiment the same as the sink level. And that way we knew that the gas pressure inside the flask is the same as outside. And so we have 2 scenarios. One, which weighs more, the gas or the atmosphere? The atmosphere weighs more. How could you tell? Yeah, because this side is a lot lower. So if this were a seesaw, it's tilted down like this. The left side weighs a lot more than the right side. Do you see that? And so what we do is we make them equal by bringing the seesaw level with the heavier side. And then we use the equation to figure it out. So were you able to calculate this? Now, the other scenario is when the gas weighs more. When the gas weighs more, it's like this. Do you know how to do that in that scenario? What we do is we equalize it to the heavier side and then add things up. And so there are going to be 3 scenarios with the open-end manometer. One where the gas is lighter, one where the gas is heavier, and one where the gas is the same. Can you do those 3? 2 of those are in the homework. Were you able to do those 2 in the homework? Then you're all right. If you could do that, then that's all you need to know. You don't need to know any kind of theory or whatever behind this. Just figure out the equations. So let's go through these here. I'll give you a little bit more time for that a little bit later. Since we're talking about this, we'll continue with this. So we try to connect things like here, law of conservation of mass. Have you made all those neural connections with other stuff? What else can you connect conservation of mass with? Anything? Lavoisier, that's good. This came from Lavoisier's experiment. He was very quantitative in his measurements. And then, where did it lead to? Think about the scientific method. What was the main topic of chapter 1? Chapter 1 is very short. Only one thing. What was it? Scientific method. So what's the next step of the scientific method? So you have observations, which led to a pattern, which led to a law, the law of conservation of mass, that's Lavoisier. And then where does it go from laws? Hypothesis and then theory. So the connection here is the law of conservation of mass led to, following along the scientific method, it led to what theory? Well, maybe the neural connections haven't been made yet, but the theory is that Dalton's atomic theory. These are the observations that led to Dalton's atomic theory. Now, you think, how could that be? Well, one of the things is, in addition to the law of conservation of mass, we have the law of, there was one more law. Do you remember the one more law? The kinetic molecular theory, that's a theory that's kind of past the law. The law is just a simple mathematical equation that kind of describes things. There's another law. It's a law of definite composition, right? The law of definite composition, the law of constant composition. That was the other thing that led to Dalton's atomic theory. Let's say you wanted, a person in California took 2 cups of flour and 1 cup of sugar, mixed it together. Are they going to get, and then somebody else in New York took 2 cups of flour and 1 cup of sugar. Are they going to get the exact same ratio to the nearest atom? You think that's going to happen? Okay, let's say one person drank water in California, another person drank water in New York. Do you think they're going to have the exact same ratio to the nearest atom, 2 hydrogens, 1 oxygen? Or do you think New York is going to have slightly different ratio? No, it's going to be the exact same. So in nature, things are kind of random collisions and this kind of stuff. When you look at kinetic molecular theory, and so the Dalton's atomic theory naturally came out of that, because if matter was infinitely divisible, then hydrogen's like flour and oxygen's like sugar. And how can you always get the same ratio each time when you have all this motion? And is that motion controlled? I mean, are they like robots and each water molecule is moving exactly the same as the other? Did you look at those? Remember the video of the water molecules moving? Were they all moving exactly the same speed, exactly the same motion, exactly the same? What were the motions? Vibrations, rotations, and were they all moving exactly the same? No. And so when you mix those kinds of things, you wouldn't expect it. And so this is what led to strong evidence, but this is not indisputable, irrefutable. It's hard because, it's like trying to say aliens exist. You need to see an alien. If you see an alien, then for sure they exist, but nobody saw an atom, right? But anyway, that's what led to atomic theory. We try to make connections when we read these types of problems. Chemists study the properties, composition, and what? Structure. In fact, this is critical because, properties are bare to measure. I mean, that's a lot of work to measure the properties. So if you can predict the properties based on the composition and structure, then you're much further ahead rather than having to measure everything. In other words, we don't want to have to memorize everything. We want to be able to use some compositional and structural data to predict it rather than having to memorize it or measure it. And so that's the connection for this. Number 3 is chapter 5. I was supposed to be in chapter 5 this week. I didn't finish it, but it's okay. I want to just make sure people are somewhat prepared, or as prepared as they best can be for exam one. We want to start off on a good foot, hopefully. Isotopes, this is chapter 5. This is chapter 2. Chemists are concerned with all these. And so if you selected all, I would have given you full credit. Because chemists are concerned with gravity, but it's not that big. The only thing gravity might affect is like at the bottom of the ocean. At the bottom of the ocean, do you think water is more dense? It is. Water is more dense at the bottom of the ocean than at the top because there's just so many pounds of water crushing down on it. And so gravitational might be important. The other things gravitational might be important is, some gases are lighter, some gases are heavier. Do you know at sea level, air has a different composition than at the top of the mountain? At the top of the mountain, because the heavy gases kind of sink to the bottom, the lighter gases can float up. And so as you go higher and higher up in the atmosphere, the composition changes because the heavier ones are down lower. But that's thousands and thousands of feet. And so their gravity might have an impact. Nuclear chemists completely ignore electrical. It turns out electrical are the most important. Do you remember the law for this? Starts with a C, end of chapter 2. Coulomb's law. So you might know a little bit about Coulomb's law. You don't have to do any calculations with Coulomb's law. You just have to know it qualitatively. But electrical forces are the most important. So if I said chemists are most concerned with, it would be C for sure. Because that's what holds water molecules together. I told you about that fountain in downtown LA with those gigantic drops of water, and they're trying to break apart, but they don't because they're stuck together. That's because of the electrical forces holding them together like the pitfalls in chapter 2. Number 7, this might be a trick question or maybe not. There is exactly 2.45 centimeters in an inch. That's false. How would you correct this? 2.54. And is it exact or approximate? It's exact, yeah. And so that's false. This one also might not be the greatest question either. Here. This particular question, maybe I don't. Because you might think that's a typo or it might be real. If this were a typo, then this would be the correct answer here. If this were real, then the correct answer would be D, none of these. And so what people did was they either selected A and thought, okay, this was supposed to be centimeter cubed, not centimeter squared, or they picked D. So I didn't care which one they picked, A or D. It would have gotten full credit. But the units were wrong, centimeter cubed. Why isn't it 2.54? It's not 2.54 because we have to cube it. So 2.54 cubed is this. Okay, which measurement is more precise? 36.0. It gives a more narrow range. We talked about that quite a lot. In addition to precision, what else do we look for? Accuracy. Which number is more accurate? You don't know, because even though it might be precise, that is high precision, lots of little increments here, it could be broken, so that it's not reading correct. And so you might have high precision, but if it's not reading correct, then it's inaccurate. And so this happens. One way people dry glass is by heating it. But if you heat it too hot, what happens to the glass? It kind of melts and softens. And so even though this is high precision, is this going to be reading accurately? And so you could have high precision, but inaccurate readings. So in order to make sure it's reading accurately, what do? Calibrate it, yeah. And so we cannot determine accuracy when we see, but we can determine precision. Yeah, this would be higher precision. So when you go through these, you want to think about, all the connections you can make. Maybe those connections haven't formed yet, but try to think of other connections on the path, because you want this path to be kind of boring, and then start thinking about other paths. But anyway, going back to this, how many sig figs are allowed in this? 2. Is that clear why it's 2? How many sig figs in this? 2. How many sig figs in 32 degrees? Infinite. Why infinite? Because this is by definition. If you go back to this, where did the 32 come from? The 32 came from the freezing point of water. The freezing point of water is exactly 0 degrees C and exactly 32 degrees Fahrenheit under normal conditions. How many sig figs are there in 9/5? The fraction here. How many sig figs in 9/5? Infinite. Also, where did the 9/5 come from? The 9 came from 180. And where did 180 come from? 180 came from 212 minus 32, delta y. 212 was exactly the boiling point of, and 32 was exactly the freezing point. And so that's exact. So we take 2 exact numbers, subtract them, we get exactly 180. And 5 comes from 100. That was 100 degrees C, boiling point of water, minus 0 degrees C, freezing point of water. Are we out of time?
Yes.
All right, so yeah, turn it in. Yeah, even if you don't finish, it's like a test. If you don't finish, just still turn it in.
For the last problem, was it a typo? Because